Well, all right, everybody, it's about 1 o'clock. I think I'll go ahead and get started. Good to see you guys. I hope that you are well today and enjoying the cooler weather that we've had this week. It's been kind of nice, I think. Um, just a couple of announcements as we kind of get started today. Um, our third midterm is actually 1 week from today on May 1st. And here again are the sections that will be covered by that exam. So the last part of chapter 4, everything about differentiation, and then this first part of the integration that we've just been working on for the last couple classes or so. So that's what the exam will cover. I haven't had a chance to grade your homeworks yet that you turned in on Tuesday, I think it was. But I'll try to get those done by tomorrow. There is another assignment that you need to be working on, and I was looking at the problems again recently, thinking these are actually really good problems. Like I think the next assignment is really good, but I also realized that, which is number 15. I also realized that I don't need to make you turn this in by Saturday if you need a little extra time. I'm doing this review session on Monday evening. So I think what I'm gonna do is I'm just gonna extend this, even if I extend it until Monday night. That'll give you a couple extra days and you can ask questions on Monday because I'll have the review session. Because I do want you to do a good job on this assignment, is basically my point. So obviously you still have plenty of other things to be doing. In the meantime, getting ready for the exam, but I'll give you a couple extra days to finish that assignment. Let's shoot for Monday. That's still 3 days before our actual exam, so you'll have all of Tuesday and Wednesday without any homework in front of you. And you can certainly do this homework, have it done by tonight if you want to. It's not that bad. So yeah, the review sessions, as I said, Monday evening, and then I might go hiking on Monday, so I might come in a little bit in my hiking getup. We'll see how much time I have to recover from that. And then on Wednesday afternoon, from 2 to 4, I realize not everybody can come, and of course it's optional. If you can't come in person, you are welcome to come in Zoom. Just go to the Zoom classroom, not the office hour room. There's 2 different Zoom rooms for this class, so go to the classroom if you are looking for me on either of these times for the review session. Or if you can't make it even in Zoom and you really are interested in what the review session has to offer, I will make a YouTube video out of the lecture and send it out to you guys after each of the reviews. So if you can't make it or don't want to make it, it's not you will still be able to get all of that material if you're interested in it. Okay. Anybody have any questions about any of that? Okay, so that's 1 week from today, our third exam. Kind of treat it like double dipping because you're also studying for the final a little bit. If you put the good effort in now, you won't have to review all of this stuff so much again, like just 10 days later. So it'd be a good idea to try to get on top of it now. Be my best advice. Okay. If there's nothing else about that, what I want to do is bring us back to where we were on Tuesday. I kind of fumbled up at the end of class with that going over that one problem from the homework with you guys. So I want to try and clean things up a little bit here and do a warm-up problem to help solidify this a little bit. And this warm-up problem is actually a harder version of a problem that is in your homework, number 15. I think there's 5 problems on that assignment, and this one is very similar to one of those 5, except this one's even harder. So if we can do this one, I think you'll be able to take the model of how that works and do the one from the homework. So, but before I get to that, here's just a summary of the main points again. I hope everybody's getting these notations figured out. The lower and upper Riemann integral, right? We put an underline or an overline, depending on whether it's lower or upper. And the lower Riemann integral, what you're doing for that is you're taking all of the lower sums. And by all of them, I mean for every partition, you can make a lower sum calculation, come up with some number for that. And what you're doing is you're taking all of those lower sums and you're taking the supremum of them. Okay, so the supremum is an upper bound, but it's the least upper bound, right? So this lower Riemann integral will be greater than or equal to any specific LPF that you calculate. So if you just willy-nilly pick a partition and calculate L of PF, you'll get a number, and you'll know that this lower Riemann integral is at least as big as that number, because it is, after all, an upper bound, right? Least, it's actually the least upper bound, but specifically it's an upper bound for all of those lower sums. Clear? You got 5 billion numbers here, right? Because there's 5 billion partitions of your interval. You calculate all those numbers, then this supremum is giving you an upper bound. It's actually the least upper bound, but it's greater than or equal to all of those. Okay, perfect. Upper Riemann integral is the exact opposite idea. We calculate all of these upper sums, right? For every partition, there will be an upper sum. And what we're looking for there is the greatest lower bound of those upper sums. So you're looking for something that would be a lower bound. And that means that this upper Riemann integral will be less than or equal to any one of these specific upper sums. Right, because it's a lower bound. Lower bound means less than or equal to everything in that set. Okay, so if you calculate any lower sum and any upper sum, you will know that your lower and upper Riemann integrals are between those values. Yeah, that's really the point. Anyway, just make sure you get these learned correctly. Sometimes people get confused about which one is the sup, which one is the inf, where's the underline, where's the overline, where's the u, where's the l. Right, so just have to make sure you get this sorted out, because if you get things mixed and matched wrong, it's really not going to make much sense. So we got to have that one right. Okay, a couple of the other results that we did last time, I talked about this idea of a refinement. If we take a partition P and we refine that partition, then the lower sum and the upper sum will get closer together. The P star is the refinement. So the L of P star will be greater than or equal to L for P, and the U of P star will be less than or equal to the U for the P, U of P. So anyway, that brings the difference between the upper and lower sums closer together, right? You're bringing on the inside here, these two numbers are closer together than the original two numbers. So this is helpful in terms of, getting closer to what the values of the upper and lower Riemann integral are. So that's the advantage of doing a partition, or doing a refinement of a partition. Yeah, so if we refine a partition, we can only improve our estimates. The values that we get will only be closer to the correct values for the lower and upper Riemann integral. Okay, so far so good? Sweet. Okay, and then I have the second proposition that we did on Tuesday. If we take any two partitions, they may not have anything to do with each other, right? They may not have common points at all other than the endpoints, but for sure, any lower sum that we calculate will always be less than or equal to any upper sum that we calculate. So even if the two partitions are ships in the night passing with no common elements in them, right? No common elements, you still can be guaranteed that lower sums are always less than or equal to upper sums. That's always guaranteed to be true. And then finally, the big theorem that we proved on Tuesday is that, in fact, this lower Riemann integral has to be less than or equal to the upper Riemann integral. And it makes sense, really, because the lower Riemann integral is you're looking at all these LPFs, right? And those LPFs are always less than or equal to the UPFs. And the UPFs are what you're looking at to calculate the upper Riemann integral. So it makes sense that this one would be less than or equal to this one. Now, if they are actually equal, if the lower and upper Riemann integrals are equal, then we're going to say that f is Riemann integrable, and the value of the integral is just this common value. Okay, so like in this warm-up problem, you see I have an integral of f from a to b that doesn't have an underline or an overline on it. That's because in this example that we're going to do next, we're assuming, or we're going to show actually, that the function is Riemann integrable. So it says show that f is Riemann integrable. So part of that is showing basically that the upper and lower Riemann integrals are the same, and therefore we don't need to put the bar on the top or the bottom. This is that common value. Okay, so does this make sense? Anything here on the results from Tuesday that has anybody concerned or any issues? Let's try this warm-up problem. Okay, I think this is a really good example, and I'm gonna try to go through this very carefully. I'm gonna take the function x squared, and I'm going to fix a to be less than b greater than 0. So maybe since I have a little space here, I could kind of draw my picture. A and b are like this, and we're looking at part of a parabola, right? It's x squared is a parabola, and on the right side of 0, it would maybe look something like this, yeah? Okay, and we're going to be looking at the interval from a to b and trying to show that f is Riemann integrable and that the value of the integral is equal to this number. So I'm actually going to try to calculate. I am going to try to calculate the lower Riemann integral and the upper Riemann integral. Okay, now a very effective way to do something like this is actually, because in theory you have to look at an arbitrary partition here, but it turns out that it's going to be good enough to just look at those P sub n partitions that I described last time. So let me just remind you how that works. We take a natural number n, I'll start the solution here, and we're going to consider the partition P sub n, right, which is an element of the partitions of A to B. Let me remind you how that works. What you're doing for that is you're chopping up your subinterval into equally spaced, you're chopping up the interval from A to B into equally spaced subintervals. So this leftmost endpoint is always x naught, the rightmost endpoint will be xn, and then in between you have, x1 and x2 and so on and so on. Okay, and there's actually a formula for what these x's are. Actually, what's going into this solution here, guys, is actually something that should be sort of more broadly emphasized in your notes. Like, because you're going to want to use this partition a lot. And so you're going to want to know, well, what is the formula for the kth point of my subinterval when I chop it up in this fashion? Well, the answer is you're going to start at A, which is the left endpoint, and you're going to add the width of each of these subintervals as many times as you need to. Now, each of those subintervals, okay, the entire interval has a width of b minus a. And I'm chopping it into n equal pieces. So if I think about how much each piece would take up, it would be b minus a over n, and this would be multiplied then by k. So this is a formula, honestly, it deserves to be in a box, actually, so that we know how that works. So if you're not totally convinced of this, try plugging in k equals 0. If you plug in k equals 0, you get x sub 0 equals a. All right, and try plugging in k equals n. So that would be the other endpoint of the interval. When k is equal to n, then the n's cancel here, and we just have a plus b minus a, which is b. So that matches the setup here. x0 lines up with a, xn lines up with b, right? And this is going to be for k equal to 0 or 1 or 2 or anything up through n. So that's the value of x of k. And then we'll just note, we've already sort of made this point pretty clear, but the delta xi's, the widths of each of them, if I subtracted two adjacent xk's, they would differ by exactly one factor of the b minus a over n. So that hopefully makes sense as well. That's just b minus a over n. Probably should put a box here too, because that's always going to be true if you're working with this partition piece of n. Okay, now I'm gonna start calculating the upper and lower sums with this partition piece of n. In order to do that, I guess I didn't recap it here, but the upper sums, as you know, are obtained by adding up capital Mi delta xi from 1 to n, and the lower sums are exactly the same thing, summation, but this time with those little m sub i's on each of the subintervals. So that's some notation from our last class as well for the upper and lower sums. So I'd like to calculate both the upper and lower sums. I think I'm going to do the upper sum first. In order to do the upper sum, I need to know what capital Mi is. So let's figure out what that is next. So let's note, we can put it down here actually. Another note, what is capital Mi? Now, what we know is that the capital Mi is the supremum of my function on the ith subinterval, right? So taking a look at this function, where is capital M1, for example? So here's my first subinterval. Where's the highest value of the function? Isn't it over here? Capital M1 is simply f of x1. And capital M2, if I go to the next one, capital M2 would be f of x2. In other words, it's simply xi, and then of course we're squaring that because that's what the function is. So this is just x sub I quantity squared. Clear enough? Okay, and then we already wrote down a formula for x sub k. Let's use it right now, guys. A plus the quantity b minus a over n, this will now be times I, quantity squared. So that would be the whole xi, and I'm just plugging in from the box here into that expression. And I am actually going to go ahead and FOIL this out, if you can believe it. We're going to just FOIL out this expression that we have. And so what is that going to be? A squared plus the cross term is 2 times a. By the way, guys, this is going to get a little messy, just so you know. Even for this very simple looking function, it's going to get a little messy, but just bear with me. It works out beautifully, I promise. So there's the cross term, 2a times b minus a times I all over n. And then the last term would be b minus a over n squared times I squared. So that's just squaring it out, what the xi squared is, okay? So it's got the a and the b in it. The one that you're doing in the homework is not x squared, it's just x, which makes it a lot nicer. It's a lot easier, it's just x. But anyway, I'm going to do a hard one just to make sure that we can do something like this. Okay, so now that I've written out what capital Mi is, I think we're ready to try to calculate this upper sum. Okay, so let's do that. So then, and again, you're going to need some room here, guys. It is going to be a little messy. I hope I have enough room. I think I do. U of PNF. Okay, so as a first step, I'll just write down the formula again. It's the summation I going from 1 to n of capital Mi delta xi. Now, one of the perks of using this piece of n partition is that all of the delta xi's are the same value. So within this summation, the delta xi, since it's the same value for each term, you can actually pull it out of the sum. So I can rewrite this, let's go to another line here. I can rewrite this as b minus a over n times the summation I going from 1 to n of m sub I. So each of those delta xi's is just b minus a over n. Okay? So now what I have to do is add up the m sub i's. Here's what m sub I is. Let's feed that in there. So this is b minus a over n times the summation I going from 1 to n. And now grab some nice big parentheses here. Inside the parentheses, we're going to put the formula that we just wrote down for capital M sub I. So it would be a squared plus 2a times b minus a over n times I, and then plus b minus a over n squared times I squared. Okay. So far, so good? Let's do one more step and then we're gonna have to go off to some side paper to remember something. I'm gonna do one more thing here, guys, which is that I'm gonna split this into 3 summations. Okay, so the first summation, I going from 1 to n, we can actually pull the a squared out of that because it's just a constant. So it's just a squared times the summation of 1. And then on the next term, I'm gonna pull out the 2a b minus a over n, leaving me with the summation from 1 to n of I. And then on the third summation, I'm gonna pull out b minus a over n squared. These are just constants. The stuff that I'm pulling in front of the summations is just constants. I am not allowed to pull out anything that has an I in it. So that last summation will just be a summation of I squared. Okay, I think I'm doing pretty good so far. We just have to put up with a little bit of messy calculation here, but I think so far so good on that. Is everybody with me? Now, let's see if we can do the 3 sums. So we've got b minus a over n. The first term has a squared times the sum of 1. 1 plus 1 plus 1 plus 1 plus 1 n times adds up to what? N, exactly. So this is just a squared n for the first term. Now on the second term, I've already pulled out a 2a and a b minus a and dividing by n. And now the next challenge for you is, does anybody remember the formula for the sum of I from 1 to n? So this would be 1 plus 2 plus 3 plus 4 up to n. Does anybody recall what that was? That's it. That's it. If you add up the first n positive integers, you will get n times n plus 1 over 2. I'm putting this up here so you can write it down because you do need to learn this. If you don't remember it, I promise you're going to see this kind of thing again. You're going to have to be able to calculate it. So let's put that in here for the summation of I. N times n plus 1 over 2. Okay, let's keep going. The third term has b minus a over n being squared out in front. And now we have the summation of I squared. So here's another one for the little note card or whatever. Does anybody remember the formula for the sum of the first n squares? So this would be like 1 squared plus 2 squared plus 3 squared. No. Could try. It's actually a little messier than that. It turns out that the answer here is n times n plus 1 times 2n plus 1 all over 6. I don't know. I got lucky. Somehow I memorized that one and it just sticks with me. But it's of course you could prove it by induction on n. But that is the formula that we need right now. And again, on the one that's in the homework, you won't have to use this one because you're not working with x squared. You'll only be working with x. But here we do need to put it in. So let's do that. We have n times n plus 1 times 2n plus 1 all over 6. Okay, so just like that. So that takes care of adding everything up. What I'm going to do next though, guys, is I'm going to simplify this a little bit. You can probably see there's some algebra here that we can take advantage of. So for example, on this first term, I'm going to go ahead and multiply the b minus a over n into each term. The n's are going to cancel. So on the first term, we'll just have a squared times b minus a. Okay, so that's the first term. Now on the next term, before I actually do anything further, I'm going to cancel the n's here and the 2's here. So there's a couple of 2's that cancel and a couple of n's that cancel. And then I am going to still go ahead and multiply the b minus a over n with what's left here. Okay, so what you'll see is that when I do that, I still have an A right here. I still have two factors of B minus A, so that'll be B minus A squared. And then the only thing left besides that is N plus 1 over N. I'll go ahead and write that down. This is just purely algebra. This is not heavy duty calculus at all. It's just algebra that we're working out right here. Okay. The third term, I can cancel the n's here. I see the n's can be canceled. Can't really cancel much else that we have up there. So I'm gonna go ahead and just feed the b minus a, which is already squared, but I'm multiplying it by another b minus a here. So it should become b minus a cubed. And then what else do we have? N plus 1 times 2n plus 1. And on the bottom, I have, oh, you know what? I made a mistake. Yeah. This n does not cancel this n exactly because it's being squared. Sorry. That's okay. So let's just uncancel that. So what it is this is actually 6n squared because there is still another n out in front here. Don't forget about that. So this is actually going to be 6n squared. There we go. All right, so I just accidentally, should not have canceled those n's because one of them is being squared on the bottom. Okay, so far is everybody with me? Okay. Now, I'm trying to decide if I want to do anything else with that or go to the lower sum first. Let's go to the lower sum. So let's just leave that as is. And let's calculate L of Pn of f and see what the difference is. Okay, we do know that the lower sum, whatever it is, will be less than or equal to the upper sum. That has to be the case. Let's just work it out. So also, or I'll just say similarly, I may not go quite as slow on this one, but it's very similar. If we do LPN of f, obviously now we're doing a summation I from 1 to n of little mi delta xi. And again, the delta xi can be pulled out as b minus a over n times the summation I from 1 to n of little mi. Now here's the question for you. What are the little mi values? We calculated the capital Mi was just xi squared, but what about the little mi? This is where the difference comes in. If we look back at our picture again, and we look at each subinterval, remember the little mi's are the infimums. So instead of looking at the right endpoint of each subinterval, which is where the maximum value would have been, we now have to look at the left endpoint. So little m1 is actually x0 squared. And little m2 is actually x1 squared. So I should note, maybe we could do it back over here, guys. I should note that the little mi is actually x sub I minus 1 squared. Right, so that's actually what the little mi would be. And I'm gonna need to feed that in my calculation here in just a second. Okay, so far so good. So how's that gonna change anything? Well, it's basically, instead of adding up, you know, x1 squared plus x2 squared plus x3 squared plus x4 squared and so on, we're actually going to start with x0 squared plus x1 squared plus x2 squared and so on. So this becomes b minus a over n times the summation, I going from 1 to n, of, now x sub I minus 1 is a plus b minus a over n times I minus 1, all of that squared. Okay. And now, at some point I was going to run out of room. Can I erase the UPNF calculation here? You guys all have this part written down, I assume. Then I'm not going to need it again. So let's just remember this was this was the U of Pn of F. I'm gonna come back to it, of course. I'm gonna come back to it in a minute. But let's just erase it for now so I have a little bit more room. Okay, so let's work on that calculation right down here. Again, I'm gonna FOIL it out, just like we did before. I'm gonna go ahead and FOIL this one out. So let's see if I can just put it right here. So this is gonna be equal, I'm gonna come right into here, I have a little bit of room. B minus A over N times the summation, I going from 1 to N of, I'm going to FOIL out this perfect square. So it will be A squared, right? Plus 2 times A times B minus A all over N times I minus 1. And then plus the square of the last part, that would be B minus A over N quantity squared times I minus 1 squared. So just like so. Excuse me. All right, and again, I want to evaluate each of these sums. I think I'm going to go a little quicker here. So here's the B minus A over N. When I add up A squared N times, that's just NA squared. It's actually the same thing that we had gotten here in the other one. Let me put it in the same order though. So it's A squared times N. And then what about adding up the middle piece? Well, I've got 2, I've got A, I've got B minus A, I've got divided by N. But now I'm adding, here's the difference. Instead of adding up I from 1 to N, I'm adding up I minus 1 from 1 to N. Which effectively means that instead of adding the first N positive integers, I'm adding from 0 to N minus 1. So that shifts our formula here. And instead of plugging in N into this formula, we effectively need to plug N minus 1 everywhere we see an N. So if I asked you what is the sum of the first N minus 1 positive integers, the answer would be, well, if I change N to N minus 1, this is how it would get shifted. Okay, and then we have one more term to go. B minus A over N quantity squared is my constant. Ooh, and now instead of adding up 1 squared plus 2 squared plus 3 squared up to N squared, I'm starting with 0 squared plus 1 squared plus 2 squared up to N minus 1 squared. So again, I'm going to shift everywhere I see an N, I'm going to write it as N minus 1. So N minus 1 times N times, if I change this N to an N minus 1, the whole thing turns into 2N minus 1 all over 6. Okay, so very similar to the expression we had before, right? The main difference is that instead of N times N plus 1, now we have N times N minus 1 right here. And over here, all of the N's have been shifted down by 1 as well. Okay, but if we now proceed to clean this up again, so the first term will again become A squared times B minus A, right? The middle term will become A times B minus A squared times N minus 1 over N. So instead of N plus 1 over N, which is what we got with the upper sum, now this becomes the lower sum. Okay? With me? And then the last term, let's see. I'm going to get a B minus A cubed again. And I'm going to get 6N squared on the bottom again. And I think on top it's
N minus 1, 2N.
Sorry, I heard you say something. What did you say?
It should be N minus 1, 2N minus 1.
That's right, N minus 1 and 2N minus 1. Thanks. Yeah, that's it. That's exactly right. Okay, so that's what we have, guys. That's what we have. Okay, so we've calculated the upper sums, we've calculated the lower sums. Any questions so far? Now we're gonna get the payoff. That was the hard work. Now we're gonna get the payoff. The payoff, my friends, the payoff is, remember, so now any lower sum, including the one we just calculated, any lower sum that we would ever put the effort to calculate is always less than or equal to the lower Riemann integral, because we're taking a supremum, which is an upper bound of all the lower sums. So this has to be less than or equal to this lower integral. And then, of course, we have our theorem 6.1 that tells us that that's less than or equal to the upper Riemann integral. And the upper Riemann integral is always less than or equal to any specific upper sum that we might calculate, such as u of Pnf. Okay, you with me? Now guys, what I want you to think about for a minute, I want you to think about this as actually not just a number, but actually a sequence that's indexed by n. So we didn't just calculate one lower sum, we calculated an entire long list of them according to P1, P2, P3, P4, and so on. This is an entire sequence of lower sums. Does it converge to anything? This lower sum here, if I let n go to infinity, let's come back in our notes here and say, what would happen to this if n goes to infinity? The first term is just a constant. The second term has an n minus 1 over n in it. What's going to happen to that? Goes to 1, right? N minus 1 over n just goes to 1. So you just have a times b minus a squared. And then the third term, again, if n blows up to infinity, I have a b minus a cubed. And what about this part here? Yeah, the leading coefficients, on top the leading coefficient is 2n squared. On the bottom, the leading coefficient is 6n squared. 2n squared over 6n squared is just a 1/3. So I'll throw that denominator of 3 in there. And I don't know if you can see it yet, but you want to know what this actually simplifies to? It's a beautiful thing. We can do a minute of algebra if we want to, or I can just tell you that this thing simplifies to 1/3 of b cubed minus a cubed. It actually does do that. So if you were to multiply, actually you could factor out of b minus a, which actually also factors out of b cubed minus a cubed. And then you can compare that with what's left over, and you will get exactly 1/3 of b cubed minus a cubed. I did it in my office an hour ago. I promise it works. Okay, so that's it. So what that means is that if I think of this as a sequence, this sequence is converging to 1/3 of b cubed minus a cubed. Right, so let's just draw this little picture because it's kind of visually helpful for us, I think. So that is what we have. The sequence is converging as such. Now, what about the sequence of the UPN of F's? That's this guy right here. Exactly the same thing. You get a squared, b minus a. This part goes to 1. You just get a times b minus a squared. This part is still 2n squared over 6n squared, which is a 1/3. It's literally the same thing, guys. This goes to the same thing. This goes to the same thing as n goes to infinity. It goes to the same thing. You with me? Now, what I have in the middle here is some value that may not look like a sequence, but guys, you can treat it as if it was a constant sequence. You can treat it as a constant sequence. So you have this sequence, you have this sequence, and you have this sequence. If the outside two sequences converge to the same thing, then what do you know about the sequence in the middle?
Converges to the same.
It converges to the same thing. It's the squeeze theorem. But what does this converge to? If it's a constant, it converges to itself, right? If I give you the sequence 5, 5, 5, 5, 5, and I say, what's that converge to? The answer is obviously 5, right? So whatever this number is, I can view it as a function of n, even though there's no n there. It's a constant, and so it would converge to the same value, meaning it would be equal to that value. Right, okay, so let's use the squeeze theorem to write that down. Does everybody follow that?
Yeah.
It's super nice. I love this problem. I mean, it's a little messy, but the idea behind it is pretty cool. Okay, so by the squeeze theorem, the lower integral of f is equal to this same value, 1/3 of b cubed minus a cubed. Now, in that comment, I'm focusing on the one on the left. But of course, this is the same deal here. This is also squeezed between the other two, the outside two. So you can say the same thing about that. So similarly, the upper Riemann integral is also 1/3 of b cubed minus a cubed. Right. And so since they're the same, what's it say over here? If they come out equal, then the function is Riemann integrable, and the value of the integral is just that common value. So we've basically finished our proof. Okay, so thus I'll just say f. F is an element of the Riemann integrable functions from a to b, and the integral is equal to 1/3 of the quantity b cubed minus a cubed. So we've now proved that very rigorously using the theory that we've developed. Yeah, go ahead, Nkosi.
Isn't that only for partitions with equal subintervals then?
It is, but the point is, we don't have to consider every partition under the sun, right? We have considered some partitions, and the point is that this thing will be less than or equal to this value, right? And this guy will be greater than or equal to this value. So to really calculate this directly, we would have to take, according to the definition, we would have to take the supremum of all possible LPFs. Okay? Why am I not having to do that? Why am I able to get away with only looking at these partitions? The reason is that I've managed just with those partitions alone to prove that if I look at the sort of the supremum of the LPN of F's, it's this, and the infimum of these UPN of F's is this, and they can't switch places, right? So these have to, if there's any other partitions that are not of this form, right, they have to fall in line with this squeeze theorem as well, essentially is what I'm trying to say.
Is that because of like theorem 6.2 where you just need one that exists?
It's kind of like that. I haven't recapped that theorem yet. I'm going to. That's the next thing we're going to do. But yeah, it is kind of based on that idea that you don't, at the end of the day, you don't have to look at every partition. By the way, I haven't put theorem 6.2 on the board yet today. The reason being that this problem actually asked me to calculate the integral. Theorem 6.2 is not good for that. Theorem 6.2, if all I wanted to do is prove that x squared is Riemann integrable, we could have used theorem 6.2 and we would have been done quite a while ago. Because it's a very nice theorem to use, but it only works on proving Riemann integrability. And then to calculate the value, we still would have had to do all of this work, you see. So that's why I wanted to go through all of this. Now, if your function, if your a and your b are both negative, that might not be a bad exercise for you guys to try. What if the a and the b are on the left side of 0? And then if you think about it, if I go through 0, if my a and my b are like this, then when you chop this thing up, there's going to be a subinterval that has 0 on it. You're going to be like, I don't know, where's my little m and my capital M? It gets messy. So one of the homework problems you guys are gonna do though for the next assignment is that you can prove what the Riemann integral is from, let's say, A to C. And then you can prove what it is from C to B and add the results. And if it's Riemann integrable on both pieces, then it's Riemann integrable on the union of those smaller intervals. So that's how you would handle it. If I said, what's the integral from -5 to 3, right? It wouldn't be quite as clean as what I've presented here, because in that case, the big M's and little m's, halfway along your partition, they change from being on the left endpoint to being on the right endpoint. You see what I mean? Because the way the shape of the parabola is. So I wanted to make this problem not too crazy. It's already crazy enough if both A and B are positive. If they were both negative, it wouldn't be too difficult either. But it's when it crosses 0 that you have a bit of a challenge with getting the explicit formulas for the big M's and the little m's. But as I was just saying, the way you would handle it is you would take that interval that crosses through 0 and break it into 2 intervals. The one on the left of 0, the one on the right of 0. You'd work on both of those separately and then use some result that allows you to glue the 2 intervals together. That's basically how this works. Okay, wow, I really like that example. So the one for the homework is a lot easier, is you don't have to do the x squared, it's just x, I think is the one on the homework. So that won't be so bad. Any questions here? Okay. So you can go tell all your friends who are taking freshman calculus that you proved the formula for the integral of x squared, and it only took you only took your professor 45 minutes to do it. And they'll be like, well, you should come to my class. We'll use the power rule backwards and have the answer in 2 seconds. We're gonna get to that. We are gonna get to that. Okay, I'm gonna state this theorem 6.2 again. I didn't put it in the recap because I just want to kind of take it from the top. This is a really important result. And so it doesn't hurt to kind of just take it from the beginning again. The assumption here is that we're going to let f be a function from the closed interval AB to R. We're going to let that be bounded. Okay, so a bounded function. So for example, if f was continuous, a continuous function on a closed interval is always bounded. That's one of your big consequences of continuity that you're studying for next week's exam. But this is not limited to a continuous function by any means. So then here's the result, guys. F is Riemann integrable on AB if and only if for all epsilon greater than 0, there exists a partition P in strict P. This is the partitions of AB, of course. I'll just emphasize that here. So it's a partition of AB with UPF minus LPF less than epsilon. So this is the result. And so yeah, as Nkosi reminded us, here we have just one partition that we have to find. We don't have to look at all possible partitions of P. So the nice thing about this result is that we can focus on finding just one partition that makes UPF minus LPF less than epsilon. The downside of the theorem is it doesn't evaluate the integral for you. So it doesn't do the second part, right? It'll show you that your function is Riemann integrable, but there's nothing in this theorem that actually gives you the value of the integral. At that point, you got to go back and think about the upper and lower Riemann integrals and what those values would be. So that's the challenge of it. Okay, so let's do the proof of this. This is not one of the double-starred proofs for your midterm next week, which basically means you're not going to need to know this proof for next week. However, on the final exam, I'm going to give you a list of theorems to learn, And this one is on that list. I'll give a short list. It'll be a short list, but this one is there because I really like this proof. It's a really nice one. So let's go through it and see if you guys like it as much as I do. Okay, so let's assume, I'm gonna go forward, I'm gonna assume that F is Riemann integrable. Okay, so that's an R of AB. And we have to prove that for all epsilon, there exists a partition. So as always, I'll do my rubber stamp here. Let epsilon greater than 0 be given. And my job is to come up with a partition. I have to find a partition here. Okay. Now, since the function is Riemann integrable, that means that this integral makes sense, right? That actually has a value. So if f is Riemann integrable, then this integral has a value, and in fact, what is it? The value of this integral is equal to the common value of the upper and lower Riemann integral. I'm going to use the lower one for this first part of this proof here. So in this case, the value of the integral is given by this lower Riemann integral. So what is that? That lower Riemann integral, now we have to really understand these definitions. It is the supremum of all the LPFs, meaning it is the least upper bound of all of the LPFs. If I take anything less than that value, it will no longer be an upper bound for all of the LPFs. I'm gonna pick something, I'm gonna make something less than this right now, guys. So if we take this integral and we subtract something from it, I'm gonna end up subtracting epsilon over 2 from it. I have now made something that is smaller than what was supposed to be the least upper bound of the LPFs. So this is no longer an upper bound of the LPFs. So this is not an upper bound of the set of all of these LP comma Fs, where P is an element of the partitions. Okay, so it's not an upper bound anymore. Okay. Well, if it's not an upper bound, that means there's some LPF that has a larger value than that thing. Okay. So if this is, I've taken something away from what was supposedly the least upper bound. So this is no longer an upper bound. So there's some LPF that's larger than that. So there exists a partition. I'm going to call this P1 because this is not going to be the final partition. I'm going to find a partition P in the P1 in the partitions of the interval AB such that L of P1 comma F is actually greater than this value that I just wrote down, the integral from A to B of F minus epsilon over 2. So there exists a partition where the lower sum is greater than this number. Okay. Similarly, if I was to have taken the integral of F from A to B and added epsilon over 2 to it, remember this integral is supposed to have been the greatest lower bound, greatest lower bound of all of these U's. The greatest one. So here's something even greater than the integral. I've added something to it. So this is no longer a lower bound for all of the UPFs. Right? So this is not a lower bound for the set of all of the UPFs such that P is in the partitions. And so, thus, just kind of mimicking what I already did once before, there exists a partition. This one will be P2. I have another partition of the interval AB, I'll call this one P2 this time, such that. Such that U of P2 comma F is less than the integral from A to B of F plus epsilon over 2. So again, this integral plus epsilon over 2 is not a lower bound anymore. So as soon as you, that just means there's something smaller than it in this set. There is some partition that gives you a U value that's smaller than it. Okay. I'm ultimately supposed to do what? Given the epsilon greater than 0, which we let epsilon greater than 0 be given, we have to come up with a partition. Does anybody have a idea how I'm going to get my partition now? The refinement of those two partitions. So I've got two partitions in front of me already. So I'm going to refine those partitions to make one single partition that I claim is the partition we're looking for. Okay, so that's exactly how this works. So let's do this. Let's let P be the common refinement of P1 and P2. So I think I talked about this on Tuesday. If you take the union of two partitions, you get something that refines both of them, right? So if I take P to be the union of P1 and P2, this will still be a partition of the same interval AB. That's exactly right. So this is the idea here. Okay. So with that in place, I just need to check what UPF minus LPF is. So then U of PF minus L of PF is what? Well, remember guys, when you did the refinement, I'm looking over there at proposition 6.1. When I do the refinement, the refined partition makes my upper sum smaller and my lower sum bigger. So this would be less than or equal to what I would have gotten had I used the upper sum using P2, because P is a refinement of P2. So just using proposition 6.1, I can replace a U of PF with something larger, which is U of P2F. Agreed? And I can replace L of PF with something smaller, which is going to be the L of P1 and F, exactly. Right? So all I've done in this step, guys, all I've done in this step is I've made the U part bigger and the L part smaller. I started with these two values, and I replaced the U value with this one, and I replaced the L value with this one. The difference has become bigger, right? But what is the difference? Oh my goodness. U of P2F was less than the integral from A to B of F plus epsilon over 2. And the L P1 of F was greater than the integral of F from A to B minus epsilon over 2. So I'm going to replace the U P2 of F with something bigger. I'm going to replace the L of P1 of F with something smaller. So again, when I subtract, it's even more than it was before. So I got a less than there, right? This difference is even bigger than it was before. And how much is that? Epsilon. Exactly. That is our epsilon, my friends. Isn't that cool? You guys don't look nearly excited at this. You're probably going to get a good chance to reproduce this one at some point. So if you have questions on it, let me know. I really like it. And that's, of course, only half of it. That's the forward direction. Still have to go backwards. Backwards direction isn't so bad. Not that that was very bad, but backwards direction is even shorter. So let's do this backwards direction, and then we'll take a little break. Okay?
P star.
Pardon? I know I was always using P star for refinement, but I wanted here to just make it look like how it's stated in the theorem. So since they're calling it P, I just wanted to call that P, but it is really the P star that we're used to seeing.
You're okay with us using the star to help us keep track?
Oh, if you'd rather, yeah, that's better for you. Yeah, if you are happy with putting a star here, there is absolutely nothing wrong with doing that. Yeah, absolutely fine. Sure thing. Okay, any other questions so far? All right, let's do the backwards direction and then we'll take a little break. To prove that f is Riemann integrable. So if I'm going backwards, I'm going to assume blah, 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 all this stuff down here. And I need to prove that f is Riemann integrable, which means I need to prove that these two upper and lower Riemann integrals are equal. I need to prove that they're equal. The way that I'm going to prove that, I already know that this one is bigger than or equal to this one. The way I'm going to prove that they're equal is I'm going to subtract them. And I'm going to show that that difference must be zero. That it actually is less than any positive number that you could write down. So in other words, I'm going to do something a little weird, which is that I'm going to start off with an epsilon greater than 0. When I say that's a little weird, what I mean is, normally when we assume for all epsilon greater than 0, there exists blah, blah, blah. Usually if we assume this, then we start off with something like, oh, let epsilon equal to 1, or let epsilon equal 1/2, or something like that. We normally pick a specific value and then go from there. To wire this proof up the way I need it to, I need to leave that arbitrary for the moment. So I'm just going to let this epsilon greater than 0 be arbitrary. So then by assumption, for the backwards direction, by assumption, there already exists a partition P with U of PF minus L of PF less than epsilon. And now we're going to do something super familiar. If we look at this LPF, remember guys, that's always less than or equal to any specific LPF will always be less than or equal to the supremum of all of them. So this is less than or equal to the lower Riemann integral of f. Remember guys, this thing here is an upper bound for all of the L's. So it's greater than or equal to all of the L's, including this one right here. And that in turn is less than or equal to the upper Riemann integral of f from A to B. And that is less than or equal to any upper sum. Okay. And so I think we're done. I mean, how far apart are these two guys? Less than epsilon, right? If I move them closer together, they're both moving in the same direction towards each other. The difference between these two guys, for sure, is also less than epsilon. If the outer two guys are a difference of at most epsilon, then the inside two pieces of this chain of inequalities has to be within epsilon as well. So clearly, if we were to subtract the upper Riemann integral minus the lower Riemann integral, on the one hand, I should point out it's at least 0. So I should have squeezed that in there. Sorry, let me write this again. I want to put 0 less than or equal to there. We already know from theorem 6.1 that that relationship is true. But this difference is less than the big difference of the outside guys, which is less than epsilon. So if epsilon is 1, that means that the difference between these two integrals is at most 1. But if epsilon is 0.1, that means the difference of these two integrals is at most 0.1. If epsilon is 0.000001, then that means the difference between these two integrals is less than 0.000001. You see, this is for all epsilon, right? So how could these two numbers not be equal? If they weren't equal, I could find an epsilon that was smaller than that difference and come up with a contradiction right now, right? So since epsilon is arbitrary, we conclude that the lower Riemann integral of f is equal to the upper Riemann integral of f. And that's what it means to say that f is Riemann integrable. So f is an element of the Riemann integrable functions from a to b. So there's the rest of your proof. Nice. Questions on that? Does it seem okay? So yeah, it's a really helpful theorem. I think after we take a break, I'll maybe work on one of your other homework problems for this current assignment by doing an example where we can directly apply that theorem. So let's take 10 minutes though, about 2:15 or so, we'll pick things back up. I'm gonna give you guys a little chance to stretch your legs here and decompress. There's been a lot of stuff going on here, so feel free to take a break. I'll give my voice a break as well. Yes, I should.
Yeah.
Oh, cool.
See you next time.
See you next class, yeah. Where'd you know him from?
I had him for problem solving the last semester.
Is he a manager?
No, I think it's actuarial.
Okay, I was gonna say, cause
Something.
the next class I teach is mostly engineering students.
Yeah, isn't that a differential?
Yeah, to be.
Yeah.
Yeah, okay.
Yeah, that's a requirement, but.
Right. I was filling in this week for another professor who I don't know if any of you know Dr. Casper. He's also an algebraist, and his wife is having a child, and they're at the hospital and everything. And he couldn't teach his classes, so he asked me if I could take over for him. So I did, and I was teaching the first class, and about halfway through, I said, "Okay, let's take a 10-minute break." And the student said, "We never get a break." I guess Dr. Casper doesn't do breaks for even his class is also 2 hours long. I'm like, I don't know if I could talk for 2 hours straight. But anyway, so they were very happy when I announced that we would
400
take.
class though? Shouldn't it be 15?
No, it's an hour, and some of the 400 level classes are
That's
just
crazy.
like this one. Yeah. So anyway, so when you're filling out your SOQs for this class, be sure you talk about how glad you are that Dr. Annan takes a 10-minute break every time. Speaking of that, I on the SOQs, not too many people have filled them out yet, so I kind of got dinged by the department. They're like, "Oh, your students aren't filling out your SOQs." So if you guys could do that, I think you have until the end of next week to fill them out. I'd really appreciate the feedback. Chances are pretty good I'll teach this class again someday, and I always learn from the comments I get. I do read them and take it very seriously. So yeah, take 10 minutes and just fill out the form. Let me know what you liked, what you didn't like, things I could improve, things I should keep doing. Things like recording these lectures. When I came back from COVID, I wasn't sure if I was going to keep recording the lectures, and the students told me, "Oh, for sure you should do that because I might want to watch it again sometime, or I might miss class or whatever." So that's something I've kept doing, mostly because of what I read in the SOQs. So definitely keep that up. So okay, well, why don't we go ahead, and I want to do a couple of examples to apply this really important theorem that we just proved, and that I think is a nice one. And one of these is kind of straight off of the next homework assignment. Actually, they're both kind of based off of something from the homework. So I think you'll find both of these examples to be kind of useful. Okay, so here is the first one. I'm going to give you a function. So I'm going to let f of x equal. It's piecewise, so it's going to either equal 1 or 0. It's going to equal 0. It's going to equal 1 if 0 is less than x is less than 1. And it's going to equal 0 if x is equal to 0 or x is equal to 1. So we're just talking about a function that's defined on the unit interval. I'm going to draw the function here. Well, actually, let me ask the question first. So the question is, prove that f is Riemann integrable on 0 to 1. This will prove that a function does not have to be continuous to be Riemann integrable. Because if we look at the way this graph looks from 0 to 1, f of 0 is 0 and f of 1 is 0. And then all of the other values, I'm going to draw an open circle along that line segment on the left and right endpoints of it. But this is the way that your picture would look. Okay? So that is the graph of the function. Obviously, it's not continuous at 0. I can't draw it without picking up my pencil. And if you tried to look at the epsilon delta definition of continuity, it would not be true in neighborhoods around 0 or 1. Okay, so to prove that this is Riemann integrable, I would like to use my theorem here, which means I'm going to need to come up with a partition that will make UPF minus LPF less than epsilon. The first line of my proof, of course, is going to be let epsilon greater than 0 be given. Well, like it so often is. But before I actually do that, I would like to think a little bit about what UPF would be and what LPF would be. So I'm not going to jump right into the rubber stamp yet. I'm just going to note that for any partition P in the partitions of the closed interval 0 to 1, if we look at what U of P comma F would equal, see, we can actually calculate it, even without knowing what the partition is. This is the summation, I going from 1 to n of capital M sub I delta x sub I. But what are all of the capital M's going to be equal to? As I chop up this interval, what's gonna be the supremum value on every subinterval? Just one, right? Even on the leftmost one, there is a value of 0 here, but you'll also catch some values of the function that are up at 1. So the point being, all of the M sub i's are equal to 1. Right, so let's just go ahead and incorporate that here. Summation from 1 to n of delta xi. I'm just gonna say this is since capital M sub I is equal to 1 for all I. All right, and what do I get if I add up all the delta xi's? I normally just get the full width of the interval, don't I? Right, so normally it's from A to B, and the interval would be B minus A, but in this case, it's just 1 minus 0, so that would be 1. So your UPF is always 1. Okay, what about LPF? Let's look at the lower sum. I know this is a little weird because we don't actually have a partition specified at the moment. So I'm trying to figure out like what will L of PF be even without specifying a partition. It'll be a summation, I going from 1 to n of little mi delta xi, right? And now I want to think about the little m's. What are the little m's going to be equal to if I chop up this domain somehow, make a bunch of chops here? Like this little m value would be what? 0, right? And so would the one on the other endpoint. But the ones in the middle would all be equal to 1, right? So the first and last term of this summation are just going to be 0 because little m1 is 0 and little mn is 0. So we could actually just change our summation to go from 2 to n minus 1 of delta xi. And so I'll give a reason here. So why is this? This is since little m1 is equal to little mn is equal to 0. And all other little m sub i's are equal to 1. Okay, so you get most of the delta xi's added together, but you are missing this first one here. So you're missing the delta x1 and the delta xn. So the first and last one, so how do I want to write that down? Well, actually, what we know is that this is x1 and this is xn minus 1. Okay, so this distance in here, which is what I'm trying to add up right now, that distance is xn minus 1 minus x1. So let's just put that here, xn minus 1 minus x1. Okay. And we don't know what x1 is, we don't know what xn minus 1 is either because we don't have a partition yet. We don't yet have a partition, so, but that's okay. So what I'm gonna do is, now I'm gonna go to my proof. And I'm gonna let epsilon greater than 0 be given, and I'm going to then construct a partition such that UPF, I can already see what UPF minus LPF is. In fact, let's write it down. So thus, UPF minus LPF is 1 minus the quantity of xn minus 1 minus x1. So that's the difference of the U value and the L value, because we calculated UPF, it was equal to 1, and then LPF was equal to xn minus 1 minus x1. So what I'm gonna basically try to do is, once my epsilon is given to me, I wanna make this whole thing less than epsilon. That's gonna be the goal. So now let's do the proof. So from here, proof, let epsilon greater than 0 be given. So now I'm ready to, you can think of everything we did up until now almost like it's scratch work. We often do, we have the scratch work first and then we go into the main proof. And what I'm gonna do, guys, is I am going to I'm going to construct a partition. Choose a partition. I am gonna do this, guys, with 3 subintervals. So let's just actually construct it very, very precisely here. I'm gonna come back to my graph. I'm gonna basically choose my x1 and my xn minus 1 to be really close to 0 and 1 respectively. And actually, sorry, it's not going to be xn minus 1, it's just going to be x2. So I'm only going to have 1, 2, 3 subintervals. And the first one and the last one are gonna be really, really skinny because that's how you're going to be able to make this thing come out less than that epsilon. So I'm going to choose x1 and x2 in the open interval 0, 1 such that when I subtract them, and notice I'm going to be subtracting them when I do UPF minus LPF. When I subtract them, I want it to be, I want to be subtracting a lot. I want this difference to be big, right? I want this to be a gaping distance between x1 and x2. And how big is it going to need to be for my proof to work? It's going to need to be 1 minus epsilon. How do I know that's what I want it to be? Oh, because if I put 1 minus epsilon here, then 1 minus epsilon will give me the epsilon that I need for the UPF minus LPF. So that's kind of the idea behind it. So we can do this. Choose x1 and x2 to be at least this far apart. Okay, great. So if we have done that, then for P equal to 0, x1, x2, and 1 for that partition, specifically for that partition, what we have is UPF minus LPF, which we already said is equal to 1 minus the quantity x2 minus x1, right? That will be less than 1 minus, so now I'm going to subtract 1 minus epsilon here instead, which is subtracting less than I did before. This thing is less than this thing, so this becomes epsilon. Okay, so we're done. We are done by theorem 6.2. Okay, I think that's on the homework, right?
Yeah.
So I gotta stop doing your homework for you, but it's okay. I try to be helpful. Everybody okay with that one? All right. Let's do one more example. This next example is actually not an example as much as it is a theorem. And I'm gonna state this theorem here, and this is actually jumping ahead in the book a little bit. So this is a result that I want everybody to know, but it's from, I think, section 6.4. But we can prove it now. And this one will also be relevant for one of the other homework problems, which is just the following statement. If F is monotone on the closed interval AB, so if you have a monotone function, then F is always Riemann integrable. So a monotone function is always Riemann integrable. Monotone, this could be monotone increasing, it could be monotone decreasing, not really sure. I'm not assuming that F is differentiable. So we're not saying that the derivative is positive or negative here. This could have lots of sharp corners on it. It's not necessarily differentiable, but it is monotone. So in this case, so let's do the proof of this. I'm going to prove that F is Riemann integrable by using theorem 6.2. So we apply theorem 6.2. And to do that, I have to start off with my rubber stamp. Let epsilon greater than 0 be given. Oh, of course, I don't want to prove both the increasing and decreasing case because they're basically the same. Let's just assume, I should have probably said this here, without loss of generality, let's just assume that F is monotone increasing. Just squeeze this back up in here. I'm sorry, I meant to write that down at the beginning. Assume that our function is actually monotone increasing. Okay. By the way, our example from earlier today with the parabola, you know, with the part of that parabola there, that would have applied to this case. So if we had done this theorem, we could have at least used this theorem to say that x squared is Riemann integrable, but we still had to do all that other hard work to actually evaluate the integral. So, but just kind of keep that in mind. Now, if it is possible that your monotone function is actually just a constant function. So if f of a is equal to f of b, then f is actually a constant function. So we need to address this case first. And we proved, or you proved, actually we proved, because we did it together on Tuesday, we proved that a constant function is always Riemann integrable. That was 6.1, problem number 1, one of the 5 problems that you turned in on Tuesday. So in this case, f is already Riemann integrable on AB by problem number 1 in section 6.1. This little integral symbol with a circle around it, so it just stands for section number. So in section 6.1, problem number 1, we would have done that. So I'm going to assume for the rest of the proof that it really is not a constant function, and that would then mean that f of a is strictly less than f of b. If f of a equals f of b, then f has to be constant, and we're already done. So let's assume that f of a is strictly less than f of b. So as we know, our job here is to come up with a partition. So I have let epsilon greater than 0 be given, and I have to come up with a partition. I'm going to use one of those p sub n's, because that'll be perfectly acceptable. And I just have to get the n right. And I'm going to pull a rabbit out of a hat here as to what the right n is. By the Archimedean principle, I can do it. So by the Archimedean principle, I'm going to find an n, a little n, in the natural numbers with n greater than, and then I have to get the right expression, which is going to be the expression b minus a times f of b minus f of a all over epsilon. Now that's kind of being pulled out of the sky. The reason is that, of course, I've already done the scratch work to know that this is what it needs to be. Okay, so this is how we're going to do that. And we're going to now consider the partition. Consider the partition, which is P sub n. This is the one where we decompose the interval from A to B into n equal spaced subintervals. And I claim that that partition will work to prove this statement. So I claim that for that n, the UPN of f minus LPN of f will be less than epsilon. That's what I'm going to show you. In order to show that to you, I'm going to need to calculate those big M's and little m's, because that's how the U's and the L's are defined. So let's take a minute to think about what the big M's are and the little m's, keeping in mind that you have a function that looks like this. It's increasing. So that's going to be the key, right? so now, on the subinterval that goes, let's say, from xi minus one to xi, we take one of our subintervals here. On that subinterval, we have capital Mi. So if I look at one of my little subintervals, right? So this is my subinterval. Question is, where's the capital Mi? It's on the right-hand endpoint of the subinterval, which would be f of xi, right? So this would be f of xi. And the little mi would just be on the left endpoint of each subinterval. That would be f of xi minus one. So those are my big M's and my little m's. This is actually a really easy proof. This is not too bad. Now I'm just going to calculate UPF minus LPF. Okay, so then UPF minus LPF. Let's see, that's a summation, I going from 1 to n of the big mi's minus the little mi's times delta xi. Excuse me. Because I'm using piece of n, each of the delta xi's has the same width, and that width being b minus a over n. That's how much the width of each of those is. And then what are we left with? The summation I from 1 to n of big Mi minus little mi. Okay, let's come back over here. If we look at that for a second, guys, this is a beautiful thing. It's absolutely a beautiful thing what happens. So this is big M1 minus little m1. Big M2, let's just write it out. Big M1 minus little m1 plus big M2 minus little m2 plus big M3 minus little m3 and dot, dot, dot. The last one is big Mn minus little mn. So just get rid of the summations and just write it like that. But would you guys agree that big M1 is the same as little m2? If you look at your subinterval, it makes even more sense. The first subinterval here, the big M1 is right here. That's the maximum value on the first subinterval. But at the same time, it's the minimum value of the next subinterval, right? Big M1 equals little m2. Cancel it. And big M2 equals little m3. And big M3 equals little m4. It's like a telescoping series, if you've seen that word before. And then big M n does not cancel. That's the one on the far right endpoint. But the little m n would have canceled with big M of n minus 1. What survives? What are the only things that did not get canceled? The big Mn and the little m1. Which makes sense because the little m1 is right here on the far left endpoint. Nothing's canceling with that. And the big Mn is way up here. And nothing's canceling with that. So what are these values? This is b minus a over n times big Mn is f of xn, but what's xn? Xn is just b, right? It's the far right endpoint of the interval. So big Mn is just f of b. And little m1 is just f of x naught. X naught is just a. So this is just f of a, like that. Okay. But we can replace f of b. So I have, do you see what I have here? I have b minus a times f of b minus f of a. that would be less than epsilon times n. This numerator is less than epsilon times n over n. So you take all of this and replace it with epsilon times n. You see that? If you move this epsilon to the other side, then b minus a times f of b minus f of a is less than epsilon times n. And this, my friends, is our good old epsilon. So there you go. If you ever run across an increasing function, you probably will find one before Monday. Then this is a beautiful theorem to use. Okay, if you want, okay, so I'll let the cat out of the bag. There is a problem on the homework for the next assignment that is a increasing function. So technically at this point, you could just, in your solution, just say, done by theorem 6.9. It might not be bad for you to kind of go through it again. Just write it out. It won't take you long to just make sure you're totally good with it. Okay? Anyway, I've done like half your homework for you now, whether you know it or not. It should be good. Question? Yeah. P1? No.
Partition is just like, it's just 2 points like the minimum.
No. The partition has n points in it. It's just that the big M's and little m's are almost all canceling out in the middle of that summation. You see all the crossing off that I'm doing over here. So maybe I should maybe make a comment here, right? So this is since big Mi is equal to little m of I plus 1, right? Yeah, big M1 equals little m2. Big M2 equals little m3 and so on. So this is for all I. That probably would be good to include. So if you look at that in the future, you understand how did all those terms cancel out? Yeah, okay. Everybody all right with that? Okay. If we're good, then I'm going to start another result. None of these results are very surprising, but I'm going to state another result. Actually, this is technically in the next section. If you decide you want to use any of this stuff between now and even on the exam, you can. But I'm not going to be writing exam questions that rely on stuff from this section because I told you this section is not really going to be on the test. Also, if you're wondering what happened to section 6.2, I'm actually skipping it. So we're going to just leave that behind and just move straight into this section here. And this is just a bunch of properties of Riemann integrals. Properties of Riemann integrals. And so we'd like to take some functions that we already know are Riemann integrable and make new ones. And so there's a proposition that we can get started with right away on this, and this is actually proposition 6.3 as well. And what this basically does is it takes two Riemann integrable functions and says, well, you can combine them together. So let's let f and g be Riemann integrable. And let's let c be just any real number. So make sure your r's don't look the same. We have the real number notation and we have the script r for the Riemann integrable functions notation. So then in this situation, f plus g and c times f are Riemann integrable. So if you add two Riemann integrable functions together, you'll get another Riemann integrable function. Or if you take a Riemann integrable function and multiply it by a scalar, it'll still be Riemann integrable. And then we, in addition to that, we have the actual values of the integrals. The integral from a to b of f plus g. As you guys know, when you do integrals, you can split up plus signs. So I can write that as the integral of f from a to b plus the integral of g from a to b. And you also have learned, I'm sure, in calculus that if you had a constant times some function, so if you wanted to integrate c times a function from a to b, we all know from our basic calculus class that constants can be factored out. And so that's exactly what this is saying here as well. We can factor out those constants. Okay, so good. So this is not surprising, of course. These results are not really terribly surprising, but they are true. I think because I only have a few minutes left, let me do the following. For the proof, I'm just going to say later. Well, it's one of the classic proof strategies, and it gets used even more by the professionals when they start publishing their papers in the journals. The first journal issue will say the proof will be coming in the next journal, and then of course the next journal doesn't come out, or if it does come out, it doesn't have it in it. It's sort of like proof by procrastination, and you never get to the proof. So I promise we are gonna do it. It's just that it probably takes more than 3 minutes to do it. Instead of doing that, I think what would be better is if I just state a couple more results here, and then we'll probably even end up done a little early here, because I don't wanna get into any deeper proofs yet. We'll have plenty of time on Tuesday to do that. So let me just leave the proof for now and just state the next proposition. And the next proposition will follow very quickly from that one. So we'll come back to proposition 6.3 later, but at least we've written it down. So if we let f and g be Riemann integrable again, but this time there's going to be the assumption that f of x is less than or equal to g of x for all x in the closed interval from a to b. So if we have one function less than or equal to the other one, then you won't be surprised that the integral from a to b of f comes out to a smaller value or less than or equal to the integral from a to b of g. So there's nothing too surprising about this. I will prove this one now, because this proof is very short based on that proof. That's the other, for decades, people didn't have the proof of Fermat's last theorem, right? It was like this famous result. But they kept proving all this stuff. Well, if this theorem is true, then we'll have this result and this result and this result. They went on and on for decades like that. I'm only going to make you wait 5 days to see the proof of the other proposition. So I'm not doing that badly. So anyway, if we want to prove this, it's really pretty easy. What we can do is we can just subtract the f of x from g of x. So g of x minus f of x would be greater than or equal to 0 for all x in the closed interval AB. And if we look at g minus f, right? So for every partition, for every p that partitions the interval AB, right? If we calculate even if we calculate the lower sum of p comma g minus f. Remember what this is. This is summation I from 1 to n of little mi times delta xi, but all of my little m's for g minus f are at least 0. So the point being, this is at least 0. Right, so that lower sum is at least 0, and thus, if that lower sum is at least 0, then the value of the integral from a to b of g minus f would be, remember, the lower sum is like less than or equal to the actual integral, always. So this would have to, if this one's at least 0, then this one's, I mean, if you really want to fill it in, you can say it's greater than or equal to L of P comma G minus F, which is greater than or equal to 0. So that much is true. And this G minus F, I realize that's a minus sign, But if you use a C value of -1 over here and put it together with, so if you take G and you scalar multiply it by a -1, then you can make this into like F minus G. And you'll have a similar result. So just using proposition 6.3. So now, by the proposition that we did not prove, the integral from A to B of G minus the integral from A to B of F is equal to the integral from A to B of G minus F. Again, you can think of this as G plus -F. And so using both of the results of that proposition together, we can use this calculation, and this is at least 0. And so if that's at least 0, then of course the integral of F is less than or equal to the integral of G. That's the whole thing. So nothing too difficult about that particular one. Yeah. All right. Well, that's about all I got for now. What do you guys think? Any questions here? We got a lot more properties to go over, so we'll have to talk about what happens if we have 2 intervals. Instead of 2 functions, what about 2 intervals? They're glued together. It's a little bit about that on the homework. And then, what about if we have a function that's Riemann integrable and we start moving a few of the points around? Does that affect the integral at all? Or does it stay preserved? So those kind of results are still in front of us. We'll mostly be continuing with new material on Tuesday. Of course, all of this stuff is relevant ultimately for us to focus on, but I hope you'll be here Tuesday for that. And then, of course, Thursday next week, we have our test. So it's kind of where we're at. I hope to see some of you by Monday, if not sooner, with office hours, questions on the homework, and the review session. All of that's coming up. Have a great rest of your Thursday, everyone. It looks like the sun has come out, so hopefully you can have a nice trip home this afternoon. Yes, the current homework assignment is now due on Monday rather than Saturday. We have a couple extra days.
For those of us
Yeah.
that showed up,
What's that?
those of us that showed up.
Yeah, exactly. I should do that, shouldn't I?